So we are using what we call the trapezoid method. So Riemann sums use rectangles. So think Riemann rectangle. Trapezoidal sum is going to use a trapezoid. So we need to know or understand our trapezoid formula. So trapezoids can take on many shapes. All of our trapezoids are going to look like the trapezoid on the screen in front of you and on your paper, where it is kind of sitting on its height, and then the bases are up in the air, and then the diagonal is at the top. So all of our trapezoids are going. All right. So rectangles are really okay approximations. So that's what we talk about. Rectangles are okay. What we noticed is on curves there was a lot of dead space, so then that dead space led to over or under estimates. So then along came this trapezoid method. And what they said was, well, if you use a trapezoid, and if you think about the area of a trapezoid, it's 1/2 the height, base 1 plus base 2. So if you use a trapezoid and we turn it so that its height's on the base, now the curved part is the diagonal of the trapezoid. So a diagonal on a curve is going to leave less open space than a rectangle. So a typical trapezoid looks like this. We typically see a trapezoid laying on its base 2 or base 1, however you want to label, and then we use the height from the inside. So what we do is we're going to just rotate that 90 degrees so that we have our new trapezoid sitting up like this. So the width of each subinterval or rectangle width is the height. The width is the height. So what we identify as the height of the rectangle is the width, or the dx or delta x in our formula. The delta x or the h, if they are evenly spaced, is the same formula for Riemann sums. So when we do a trapezoid area, there are two cases. There are going to be the cases where the height is uneven intervals. So then we have to treat it like we did the uneven intervals of a Riemann sum. What's really nice is if you have a trapezoid with even intervals, then we have this like sheet formula we can use to make it easier. So it says use 4 trapezoids to approximate the area under the curve, starting at 1 and ending at 3. So we're starting at 1, we are ending at 3. I need 4 trapezoids, so that means that my height, or my delta x, is equal to 3 minus 1 all over 4. Or 1/2. Just like in our previous units, if I need to break this base area into 4 subintervals, I am going to need the heights at 5 points, because you have your beginning, your end, and the midpoints in between. So that means I need to know f of 1, f of 1.5, 2, 2.5, and 3. So 1 plus 2 is 3, 3 minus 2 is 1. Points. Fractions. 3 halves squared is 9 fourths. 9 fourths plus 2. .25 plus 5 fourths. So, just like a Riemann sum, if the base height is the same, we can GCF it out. So the area, using the trapezoid formula, is the area of a trapezoid, which is 1/2, times the height, which is 1/2, times the sums of the bases. So it'd be 1/2 times 1/2 times your first trapezoid, which would be from 1 to 1.5. So now 1 is at 1, 1.5 is at 1.25. And then you would add to that your next trapezoid. But again, if you think about the trapezoid formula, it's going to be 1/2 times 1/2 times the bases. So what you can do is factor out those halves. Does that make sense? And then you just have to multiply all of that by the sums of the bases. So then my next trapezoid would be starting, so now I have an overlap, right? Before, none of my rectangle sides overlapped. Now, the trapezoid side here starts at 1.5 and goes to 2. Plus the next trapezoid, which starts at 2 and goes to 2.25. So again, can you see how all of these trapezoids are much closer approximations than a Riemann sum? The last rectangle usually ends here, but now it starts where we ended and goes to where the whole interval ends. So I have my last trapezoid that starts at f of 2.5 and goes to f of 3. So what do you notice about the numbers you're summing inside when the trapezoids share the same height bases? So what happens is all of the interior bases are summed together heights. So if you're doing this without a calculator, you could say, okay, half times height times the first input value plus 2 times all the interior input values. And then the last. So you double all of the sides, and what you can see, and why I tried to highlight them in different colors, is this overlapped. It was in the green and the blue trapezoid. This was in the blue and the purple. This was in the purple and the orange. So those interior heights or bases overlap. So we end up getting, for our final answer, 1/4. So you have a 4th times 19 or 19. Which is 4.75. And if it didn't have units or it asked you for units, this case would be units squared because you found area. So what's different from this example, from the last example, is my intervals are not even. My first one is 0 to 1, my next one's 1 to 3, my next one's 3 to 6, and I go to 6 to 7. So you can't factor out your heights in this case because they're all different. So rectangle or trapezoid height, depending on what method you are using, in this case is 1, then 2, and 3, and 1. So I always like to do that so I don't cube it up. So then it says use RAM. So I'm doing right rectangles. So I'm going to say, all right, well, it's base times height, so 1 times 2, because it's the rightmost endpoint, plus 2 times 5, plus 3 times 10, plus 1 times 13. So then I have 2, 10, 30, 13. 10 and 30 is 40. 40 plus 13 is 53. 53 plus 2 is 55. So that's my RAM. I want to compare that answer or estimate with my other problems. So this time I have units though. So base is minutes. Height was velocity, which was centimeters per minute. So all of these in terms of units were minutes times centimeters per minutes. So the minutes canceled and this answer would have been in centimeters. My answer would have been in centimeters. So same rectangles, same widths of 1, 2, 3, and 1. Now I am looking at LRAM. So I'm going to start with all of the heights. And this one I get 30 centimeters. So 30 to 55 is a pretty big difference when we're talking about total distance. So we look at those and we say, all right, LRAM, RRAM, bad interpretations of this data. Let's do it one more time using my trapezoid method and see what we get now. So, once again, I have one rectangle whose height is 1. So my first rectangle is going to be 1/2, a height of 1, and I'm going to add my bases together. So really what you're doing with that 1/2 in the trapezoid is averaging your base heights. That's what that 1/2 in the trapezoid does. It averages those base heights. Your next trapezoid has a base of 2. So we have 1/2, 2, and my base heights are 2 and 5. One half, my height is 3, and my base heights are 5 and 10. And then last, 1/2, height 1, and my base heights are 10 and 13. So all of them have a half, so you can actually still factor out that 1/2 if you want. So maybe I don't want to have fractions as I go. So 1 plus 2 is 3 times 1, plus, I took away that half, so 5 plus 2 is 7, 7 times 2 is 14. 5 plus 10 is 15, 15 times 3 is 45, and 10 plus 13 is 23, 23 times 1 is 23. My hope is that when I add these together I get an even number so it's easier to divide, but you never know. So 3 plus 14 is 17. 17 plus 23 is really nice. So we end up getting 30 plus 10, which is 40. And then 40 plus 45 is 80. 85 is not even. So I'm out of the problem. Doesn't divide nicely. But 85 divided by 2 is 42.5. So we have 42.5 centimeters. Thanks, Nick. Yes, you did. It's under your chair, honey. Thank you. You're very welcome. Good. And then the last one. So it says the following table shows the speed in miles per hour of a cyclist. Use the trapezoid to find the distance the cyclist traveled in a 12-minute time interval. So once again, what's my problem? I have minutes and miles per hour. So are they compatible units? No. So you have two choices. You can take your final answer and divide it by 60, or you can change all of your minutes now. So neither one is right or wrong. It's more or less, are you going to remember? So if you notice it when you read it, then I would change it. Or I would mark it, circle it, highlight it. I would do something so that if you are rushed when taking a test, you don't forget it. Like, that's the thing. Like, it's fine to save it for the end, but when we save it, we tend to forget that we saved it. So for me, these are all just divided by 60. to be out in front for all. Do your width for the middle one. So from 0 to 2 is 2. Now it's 2/60ths. Times 33 plus 25. Plus the distance from 5 to 2, which is 3/60ths. 25 to 27. Plus 5 to 6, which is 1/60th. 27 plus 13. No, I'm going to calculate this. Honestly, I think this is a non-calculator question. Plus 6 to 9, which is 3. 13 plus 21. 9 to 10 is 1. 21 plus 5. And then 10 to 12, which is 2. 5 plus 9. So 33 and 25 gives you 58. 2 and 60. See, I'm not going to cancel my 60s because they all have 60s right now. So, kind of even like the 1/2, like you could pull that 60 out in front. So maybe that'll make you feel better. So 30 and 20 is 50, 55 times 2 is 110. Ah, 58, thank you. Debating, oh my, stuff was hidden. Alright. 25 and 27 is 52. 52 times 3 is 156. 27 and 13 is 40. 13 and 21, 34. 34 times 3. Alright. Technically, that's a numerical answer, and AP would accept it if it was a non-calculator question. And actually, not sure you couldn't stop your answer here for AP on a non-calculator question. If my time was running low, I would write that. I would throw my units at the end of it, and come back to this if I was running low on